First of all, let me thank the Department of Naval Architecture and Offshore Engineering of the Academy of Maritime Education and Training, AMET, which is at Chennai. And let me take this opportunity to thank uh, Professor Colonel Dr. G. Tiruvasagam, the Vice Chancellor of AMED, and Dr. Lily and others who have organized this one-day national seminar on coastal hydrodynamics and structures. Uh, and I also thank the organizers for giving introduction to me. And I'm a little, what shall I say, hesitant in the sense that the topic given to me is introduction to wave hydrodynamics. Okay. So now this introduction to wave hydrodynamics is such a topic. It is more like a classroom session of wave hydrodynamics. Now, I have a very brief content, that is, we will discuss about this wave motion, and in this we will talk about linear wave theory. Okay, of course there are non-linear wave theories as well, but linear wave theory is good enough for most practical purposes, except when you have very requirement where you need to consider the non-linearity of the waves. And in this wave motion, we will derive what is called as the dispersion equation. And then we will look at how much wave energy is carried per unit wavelength. And then a brief glimpse of wave transformations. Yeah. So I am not touching upon the structural aspects because I think there are speakers to follow me who would touch upon the uh, structural aspects of this offshore engineering. Okay. So now, if you look at the classification of the spectrum of ocean waves, and according to the wave period, you have different types of waves. Okay. So on the x-axis, you will see that wave period in seconds. So now if the wave period is of the order of 0.1 second, yeah, very, very low wave period. Now these waves are capillary waves, yeah, below this. Then you have ultra gravity waves, and bulk of the waves is what we call as gravity waves, where the wave period roughly is between 1 to, let's say, about 25 seconds. So this is the period, and this is where we focus mostly, because if you look at the spectrum, the energy content in this ordinary gravity waves is much large. And then you also have the harmonics like the infragravity waves, then the long period waves. And then you also have, you know, waves due to this tides, etc. Yeah, astronomical influence. So you have the ordinary tide waves. It could have a period of about 12 hours or 24 hours. So this is the classification of the wave theories. And then we would be basically looking at the ordinary gravity waves, which are, okay. So now, if you look at a general wave, yeah, so in the deep sea, so this is the dotted chain line, which, let's say, gives you the calm sea level, okay. And due to the way wind action, what happens is that the surface is disturbed. And then there is an imbalance between the surface tension and the gravity. Okay. The surface tension tends to pull the water surface to a horizontal, this one, whereas the gravity tries to pull the force downward. And because of this unbalance, you will see that the waves are generated. And this is a typical sinusoidal wave, where you have from the crest to crest, you have the wavelength, and then you have from the crest to the trough, wave height, the amplitude, and then any excursion of the surface from the still water level is we denote it by eta. Okay, so this just briefly gives you the picture of how waves are generated. And as I told you, that there is a imbalance between capillary forces and gravity forces. This is what creates the uh, waves due to the disturbance of wind, etc. And you know that waves are like unending all throughout the year. You get waves, and a lot of effort is being now focused onto how to tap this energy that is carried by the waves. So wave energy converters are very popular these days. A lot of people are looking into this wave energy converters. Of course, I'll not be touching upon the wave energy converters as such. I'll be only focusing on wave hydrodynamics. Okay. Now, this is a picture or a graph of the relative height, sorry, the depth of the thing and the wave height. So you have h over gt square plotted against small h over gt square. This small h is the depth of water, and this h is the height of the wave. And this is a diagram after the author Le Mahotte. And here you will see that different wave theories are applied at different regions. Okay. So when the depth of water is small, then you have shallow water waves. And in shallow water waves, you have what are called as sinusoidal waves, and then you have solitary waves, and so on. And as the height goes on increasing, then the wave becomes unstable and it breaks at a limit of h by h of roughly about 0.8. Okay. And then you have intermediate depths. So here also you have the waves and deep water waves. Generally, the linear wave theory is developed for deep water waves, but it is also applicable in this region. So here for intermediate waves and up to this point, you can see that you can have this linear wave theory. And then you have the higher order waves like the Stokes second order, third order, fourth order, and fifth order waves. Like here you have the small amplitude waves or the airy wave theory. And these waves are purely sinusoidal. Okay. Whereas when you have this higher order waves, so what happens is that the height of the wave goes on increasing, and because of the increase or rather the decrease in the depth, then there is an effect on the trough region. So you'll see that the trough gets flattened, whereas the peak gets sharper. And these types of waves are the sinusoidal waves. And further, you could also have solitary waves. So Stokes waves, sinusoidal waves, and solitary waves we would not be touching upon. So we will only talk about the small amplitude airy waves. Okay. Now, the theory for this small amplitude wave theory is basically we will be looking at what is called as an inviscid flow theory. Yeah, so inviscid means the fluid is non-viscous and it is incompressible. Okay, so for non-viscous and incompressible, we will also make an assumption that the flow is irrotational. Okay, so when you say that the flow is irrotational, it means that the cross product of del and u is 0. So first, let's take this continuity equation, which is nothing but conservation of mass. So del dot u is equal to 0, where u is the velocity, which is given by its components in the x, y, and z direction, and u in any direction. So the subscript m indicates any direction. It could be x, y, or z. And phi is the velocity potential. So this is the definition for the velocity in terms of the velocity potential. You take this and substitute back in the continuity equation. You will end up with the Laplace equation, which is nothing but del square phi by del x square plus del square phi by del y square plus del square phi by del z square is equal to 0. So now this Laplace equation is called as a linear equation because it has two properties, that is it is invariant, and the principle of superposition is applicable. That means you can combine the solutions and still get the solution of the larger problem. So you can break down the problem into smaller problems and then sum it up. So that is why it is called as a linear equation. Now, instead of using the velocity potential, you could also use the stream function psi. So the stream function psi can be substituted provided you have this condition of irrotationality. So which is nothing but the cross product of del and u is equal to 0. And for this y component, you will get that del w by del x minus del u by del z is equal to 0. Substitute for w and u in terms of psi, you will end up with the Laplace equation in psi. So whether you use the Laplace equation in phi or psi does not matter. You can still get the same answers. Okay, but many of the books start with uh, the velocity potential Laplace equation. So we will stick to the velocity potential in for the Laplace equation. Okay. Now here, this is the problem that you have the governing differential equation. So what is the governing differential equation? It is del square phi equal to 0, which means del square phi by del square phi by del x square plus del square phi by del z square is equal to 0 is what you're trying to solve. So it is a partial differential equation of second order, and it has to satisfy certain boundary conditions. And what are the boundary conditions? You have the boundary conditions like the bottom boundary condition. Then you have the, here it is, so you have the lateral boundary conditions on either side of the wave. Then on the surface, you have the kinematic free surface boundary condition and the dynamic free surface boundary condition. And also on the bottom, you have the bottom boundary condition. And this is a kinematic requirement. And here, the XY plane is in the horizontal, whereas Z is in the vertical direction. So you have the U component and the W component. So this is the definition sketch of the problem. Now, let's look at this kinematic boundary condition. So what does this kinematic boundary condition say? Is that d by dt. So this capital D by dt indicates that it is the total derivative. So using the chain rule, you can write, okay, so now this F is any equation of a streamline or a boundary. Okay, so this F could be a function of xyz, which is space coordinates, and it could also be a function of time coordinate t, which means that the boundary could be moving. Okay, so in that case, you can use the chain rule del f by del t into dt by dt, which is 1, then del f by del x into dx by dt, which is u, then del f by del y into dy by dt, which is v, and del f by del z into dz by dt, which is w. Okay, so this derivative is called as a local derivative, and these other three derivatives are called as a convective derivatives, okay, or advective derivatives. And this should be equal to 0 on the surface xyz t equal to 0. So this is the kinematic boundary condition. So you can rearrange this, take the del f by del t on the left hand side. And this terms, the convective terms, can be written as u dot del of f. That means first you need to take the dot product of u and del. And what is del? Del is nothing but the gradient operator, which is defined by del by del x of I plus del by del y of j plus del by del z of k in the Cartesian coordinates. Of course, we'll be sticking only to the Cartesian coordinates. So other curvilinear coordinates we'll not be considering. Now this del f itself is a vector, okay, and it has a normal, okay, and it has its magnitude. So del f absolute value is the magnitude, and with this you can get the definition for n, which is del f by magnitude of del f. So u dot n you get minus del f by del t over the magnitude of del f on the free surface, or on the sorry, not the free surface, on the surface of the boundary, okay, of interest. And del f, of course, by definition is root of del f square, del f by del x whole square plus del f by del y whole square plus del f by del z whole square. Okay, so this is about the kinematic boundary conditions. Okay, then you have the bottom boundary condition. So generally you will have the bottom to be of some nature like this near the beach, okay, and maybe at the deep sea you can take the bed to be horizontal, okay. Now this f is a function of x and z. That means you are looking at the equation for the bed. So this will have a value of x and z, and that would be equal to z plus h of x equal to 0. Okay, so that is, you have u into del h by del x plus w equal to 0 on z is equal to minus hx. Why minus? Because you are taking the positive z is in the upward direction. So since you are moving in the downward direction, you are taking this term to be minus, and then use this unit vector definition and get this thing, and you will end up with a equation of this form: w by u to be equal to minus dh by dx. Now this is very interesting in the sense that this is nothing but the equation of a streamline of the bottom. Okay, so this bottom, this is the equation of a streamline. So the bottom satisfies the equation of a streamline. So any solid surface satisfies the condition of streamline, because a streamline is defined as one such that the velocity, sorry, the tangent on the surface gives you the direction of velocity, and the normal velocity is 0. Yeah, so that, because we are considering inviscid flow, we are not imposing the no slip boundary condition. In actual practice, what happens is that at the boundary the velocity has to be 0, since we are considering or we are neglecting the effect of viscosity and we are considering ideal fluid. Then the velocity at this point is nothing but the tangent at this point. So it has a component of u and minus w, and that is why this minus sign comes. So this is about the bottom boundary condition. Okay. Then you also have two boundary conditions on the free surface, which is, one is called as a kinematic free surface boundary condition, and the other one is the dynamic free surface boundary condition. Yeah. So here you will see that you have to write a equation for the free surface itself. So what is the equation for the free surface? It is z minus eta is equal to 0. And what is eta? Eta is a function of x, y and t. Why x, y? X is in this direction of propagation and y is the lateral direction. And xy is nothing but the horizontal plane. And since wave is a dynamic motion, it is also a function of time. So to write the expression for the free surface, you are writing it as z equal to eta of xy t, and then you take the eta on the other side and express it as equal to 0. Then you can carry out a similar process that u dot n is equal to nothing but del eta by del t of, yeah, divided by this term del eta by del x square plus del eta by del y square plus 1. So that minus sign goes because you already have a minus here. Okay. So on z equal to eta y and t, then the unit normal vector is obtained by this expression. And when you finally substitute, you would get the kinematic free surface boundary condition as W. So what is W? It is nothing but the velocity component in the z direction, which is equal to del eta by del t plus u into del eta by del x plus v into del eta by del y. So you can see here that these two terms are nothing but the convective terms, and this is the local derivative of the displacement of the free surface from the still water level. Okay, so this is the kinematic free surface boundary condition. Similarly, we can have the dynamic free surface boundary condition. And for this dynamic free surface boundary condition, we need to use the energy equation. And what is the energy equation? It is nothing but the unsteady Bernoulli's equation. Okay. And always remember that Bernoulli's equation is again applied only to streamlines. Okay. And just like your bottom boundary condition satisfied the condition of a streamline, the free surface also satisfies the condition of streamline. Okay. Therefore, we can use this Bernoulli's equation, which is the unsteady Bernoulli's equation, which is nothing but minus del phi by del t plus half of u square plus w square plus p at eta over rho plus gz is equal to a constant which is a function of time. So this is the unsteady Bernoulli's equation. And for u and w, you can substitute the definitions from the velocity potential. So u is equal to minus del u by del x, and w is equal to minus del phi by del x, and w is equal to minus del phi by del z. And when you square it, it will become plus. So you substitute this, and this has to be substituted at z is equal to eta x t. So this is the dynamic free surface boundary condition that is substituted here. Okay. And then you also have the lateral boundary condition. So take this case of a simple wave generator in a lab. Okay. So if you have a hinged paddle which performs the simple harmonic motion, then you will see that the wave is generated, and of course it gets absorbed on the beach. Okay. So here we will be applying the lateral boundary condition for the wave maker. That means for the paddle. So for the paddle, what is the equation? The equation is x is equal to s of zt. Okay. So this s of zt is nothing but the displacement of the paddle with respect to the this thing here. Okay. So with respect to the initial position. Okay, so you have again substitute for u dot n as del s by del t over root of 1 plus del s by del z square. And finally, you will end up with the expression of this type, that del s by del t on x is equal to sz is equal to u minus w into del s by del z. So these are the lateral boundary conditions. So just to recap, you have the boundary conditions like the kinematic boundary condition, then the bottom boundary condition, the kinematic free surface boundary condition, and the dynamic free surface boundary condition along with the lateral boundary condition. So these are the boundary conditions that need to be applied for the problem. Okay, so let's go to the, of course, you also have another this thing that for waves that are periodic in space and time, it should also satisfy the condition that it should be periodic in space in the sense that phi of xt is equal to phi of x plus L and t, and it should also be periodic in time in the sense that phi of xt should be equal to phi of x t plus t, where t is the wave period and L is the wavelength. Okay, so to summarize, this is what you have. So what you have is the governing equation, which is del square phi is equal to 0. So we'll be considering one wavelength, and then we take the bottom boundary to be horizontal. Okay, so which means that it could be in deep sea or whatever. Yeah. So here you have minus h. So minus because your origin is at the still water level. So you are measuring in the downward direction. That is why minus. And z is between eta. Eta is nothing but the excursion of the water surface from the still water level. So this would be eta and h. So this is the range. So you have the periodic lateral boundary condition on the two sides, the bottom boundary condition, and then you have the kinematic free surface boundary condition and the dynamic free surface boundary condition. So this is the summary of the thing. So now let's look at how to solve this problem. Okay, so now the method that is adopted is called as the method of separation of variables. And as I told you that this method of separation of variables is possible because your governing equation is linear. That is, your del square phi is equal to 0 is a linear equation. Therefore, we could have the combination of solutions in the sense that you could have phi of x z t to be equal to some function of x, capital XX, then capital ZZ, and capital TT. So these three are taken. And the first thing is we will look at this function, which is should be a function of t. So we have now sine sigma t to be equal to sine sigma t plus t. Yeah, that is, you have a periodic function, isn't it? So you could also write this as sine sigma t to be equal to, you can expand it using the trigonometric relationship, and which satisfies. So therefore, you take this phi of xzt as xx zz and then sine sigma t. So your t of t is nothing but sine sigma t. Now take this and substitute in the Laplace equation, that is del square phi by del x square plus del square phi by del z square is equal to 0. Then when you substitute, yeah, so you would get this equation del square by del x square of x into z of z sine sigma t plus x of x del square by del z square of z into sine sigma t equal to 0. So this is your Laplace equation when you substitute this function here. And you can divide by phi and get 1 over x del square x by del x square plus 1 over z del square z by del z square is equal to 0. So now if this has to be 0, then you have two components, isn't it? 1 over x del square x by del x square and 1 over z del square z by del z square. So these two components should be equal and opposite. Then only it is equal to 0. Therefore, we choose two constants. One is minus k square and the other one is a plus k square. So these are equal and opposite. So when you substitute back in this, it will satisfy. So therefore, now we have two differential equations. One is del square x by del x, del square x by del x square 1 over x equal to minus k square, and del square z by del z square 1 over z equal to plus k square. So now this are solved, okay, by using differential equations knowledge, and you can get the solutions of this nature. Okay, so the character of k, then it could be real. So when it's real, k square is greater than 0. So when k square is greater than 0, when you substitute when you use this, the solution would be a cos kx plus b sin kx. And For the second equation, it would be z of z is equal to c e to the power of kz plus d e to the power of minus kz. So, of course, the others we will not consider now. Then you substitute. So you will see that you get a function phi to be equal to a cos kx plus b sin kx into c e to the power of kz plus d e to the power of minus kz sin sigma t. So how many constants we have? You have four constants now, a, b, c and d. And why you need these four constants? Because you have the differential equation of the type del square phi by del x square, for which you need two boundary conditions, and another two boundary conditions are for del square phi by del z square. So totally four boundary conditions. So you have four constants here which can be determined. Okay. Now, the first thing is that when you apply the periodic boundary condition, so that is a cos kx plus b sin kx should be equal to a cos k of x plus l plus b sin k x plus l. You can expand it. This will be satisfied only for the condition that cos of KL should be equal to 1 and sin of KL to be equal to 0. And this is possible for the value of KL to be equal to 2 pi, or K is equal to 2 pi by L. And this K is called as a wave number. So this is the definition for wave number. Okay. Then you impose the bottom boundary condition. And what is the bottom boundary condition? That W is equal to minus del phi by del z should be equal to 0. So when you differentiate this function, rather, yeah, when you differentiate this function and then substitute, you will get, now you will see here that all these a etc are all these constants except for this term in the bracket. So only when this term in the bracket is equal to 0, then this is satisfied. So when you impose that condition, then you will see that c would be equal to d into e to the power of 2kh, because when you substitute z is equal to minus h here, so this is the condition that you would get. Okay, and substitute back, then you will get the function phi to be equal to g cos kx cos hyperbolic of kh plus z into sine sigma t. Okay, so this is one function. You have function of x, then you have a function of z, and you have a function of t, and this g is equal to 2a d e to the power of kh. Then we apply the dynamic free surface boundary condition, and this dynamic free surface boundary condition is nothing but you want to apply the Bernoulli's equation for z equal to eta. And remember, we had already said that Bernoulli's equation is applied only for the streamline. Okay, and since free surface is also a streamline, we are applying the Bernoulli's equation for the free surface. Now, since we are taking some small amplitude wave theory, we can expand this Bernoulli's equation itself by using Taylor series. And what is the Taylor series? The Taylor series is nothing but Bernoulli's equation at z equal to eta is nothing but the Bernoulli's equation at z equal to 0. That is the Bernoulli's equation at still water level plus the higher order terms. So since eta is the eta is the displacement of the free surface from the still water level, eta into del by del z of Bernoulli's equation at z equal to 0 plus higher order terms. So higher order terms we are neglecting, and you substitute this thing here, Bernoulli's equation. So of course we use the unsteady Bernoulli's equation, gz minus del phi by del t plus u square plus w square by 2 at z equal to eta is equal to, you we simply write gz minus del phi by del t plus u square plus w square by 2 at z equal to 0 plus this term eta, and when we differentiate within the braces, you will see that you get g plus del square phi by del z del t plus half of del by del z of u square plus w square at z equal to 0 is some constant which is a function of time. So when you carefully look at these things, when you have the pressure is equal to 0 on z equal to eta, that is because atmospheric pressure, isn't it? So when you substitute that, then that term p goes in this, yeah, this p by rho term would have been there, so that goes off. So here when you substitute z equal to 0, this term is 0, then you have this minus del phi by del t that remains, and u and v are very small values at z equal to 0, so this gets neglected, and the next term is g into eta would be there, and here since you have del phi by del z, which is nothing but w, that term is negligible. So this two term also gets neglected, and simply you get minus del phi by del t plus g eta at z equal to 0 equal to c of t. Now we need to determine this c of t, and how it is done is that when you take the average value over one wavelength, then naturally that constant would become 0. So that is what is done, and what you would get is that you get eta to be equal to h by 2 cos kx cos sigma t, and g, this term here is nothing but hg by 2 sigma cos of kh, and you get value of phi which is equal to hg cos kh plus z over 2 sigma cos kx into sine sigma t. So this is the velocity potential that you would finally get. And the next thing is you apply the kinematic free surface boundary condition just as you had applied the dynamic free surface boundary condition. So from the kinematic free surface boundary condition, we still use the Taylor series, that the kinematic free surface boundary condition at z equal to eta is nothing but the kinematic free surface boundary condition at z equal to 0 plus eta into del by del z of the kinematic free surface boundary condition at z equal to 0. So when you look at this, then at z equal to 0, del eta by del t and yeah, so this w remain, and you simply get w equal to del eta by del t. Okay, and w is nothing but minus del phi by del z. So substitute this. So here you have now a function of phi, del phi by del z, and del eta by del t. So this phi and eta are here. So you have the phi and sorry. Yeah, and you have the expression for eta. So take this eta and phi, differentiate it, differentiate phi with respect to z, and differentiate eta with respect to t, and equate it. You will get the final solution as sigma square is equal to gk into tan hyperbolic of kh. So this is the all important dispersion relationship. Okay. So any small amplitude wave theory, this is the equation that you are trying to solve. And what is sigma? Sigma is nothing but 2 pi by t. Okay. And what is k? K is nothing but the wave number, which is 2 pi by L, where L is the wavelength. And what is h? H is the depth of water. Okay. So now you have this hyperbolic function, tan hyperbolic of kh. Now it's not very easy to solve this problem, this equation. Why? Because k is occurring within the hyperbolic function, and k is also occurring here. That means 2 pi by L is occurring on either side. Although sigma can be taken to be constant because of constancy of wave period, which means that for any wave with a wave period, whatever be the wave transformation, the wave period is not going to change. Okay, but here the wavelength L can change, isn't it? So therefore, to solve this, we use different methods like Newton-Raphson method and so on. And to make things easy, you have the wave tables. Okay, so the wave tables that are available basically give you the solution for this dispersion equation. Okay, so that is why the wave tables are provided, so that you don't have to do this iterative solutions. Okay, so because this is a implicit equation, so this is a all important equation for small amplitude wave theory, and this we got it by solving the governing equation del square phi equal to 0 by applying the bottom boundary condition, then the lateral boundary condition, then the kinematic free surface boundary condition, and the dynamic free surface boundary condition. And finally, this is what you get. Okay, now, uh, like as I told you that this is a implicit equation, you could also solve it graphically in the sense that if you plot this uh, sigma square h by g kh for sigma square h by k equal to this thing. So you'll get one curve and then the tan hyperbolic kh, another curve here. So you'll see that the tan hyperbolic kh becomes asymptotically equal to 1 for large number of kh. And where these two curves intersect is the solution. Okay, so this is one way of looking at it. Okay, so if you have a graphical plotter, you could plot this and then get. So this is one way to find the root to the dispersion equation. And there are asymptotic values. So for the function cos of kh, for large kh, it is equal to e to the power of kh by 2. And for small kh, it tends to become 1. So here you have the cos function. Okay. And for sine hyperbolic kh, for large kh, again it is equal to e to the power of kh by 2. That means for large value of kh, you will see that both sine hyperbolic function and cos hyperbolic function are similar. Okay, very little difference. Okay, whereas when you look at this thing, so here you have the tan hyperbolic kh for large values, it tends to become 1, and for small kh, it is almost equal to kh. So these are some asymptotic values that can be used for solving this equation. Okay, dispersion equation. Now we will quickly look at the kinematics. So water particle kinematics, eta is equal to h by 2 cos kx minus sigma t, and phi is equal to minus h by 2 g by sigma cos k h plus z by cos kh sine of kx minus sigma t. So you take this and use the dispersion relationship, substitute for sigma here, and you would get this value is c. And c is called as a celerity of the gravity wave, and which is nothing but your sigma by k. Okay, so sigma is nothing but 2 pi by t and k is 2 pi by l. So if you substitute, you would get a l by t, and that gives you the value of the celerity of the wave. Okay, and with this value of phi, you can find out what would be the velocity in the x direction and what would be the velocity in the z direction. So you can differentiate it with respect to x, and then you get an expression for the velocity u. And similarly, you can differentiate it with respect to z, and you get the component in the z direction, that is the w component. So again, if you differentiate, you would get differentiate it with respect to t, then you will get the acceleration in the x direction, and similarly you will get the acceleration in the z direction. And these accelerations are important because they may affect the pressure distributions. Okay, so here if you look at the uh, water particle velocities in a progressive wave, so here you will see that under the crest you will have positive values of the velocities in u, and under the trough it is in the opposite direction. Okay, so you have the velocities increasing up to the free surface, and here the velocity is in the upward direction, that is a uh, W component. Okay, and you will see that, of course, it's not very visible in the sense that the W component, the arrow sizes are small near the bed, and when you go towards the free surface, the arrows increase, which means that the magnitude of the velocities goes on increasing as you go towards the top here, and then below this point you don't have the horizontal component, and similarly below this point you don't have the vertical component. So here it is purely horizontal component. In between you would have both the components. In between you would have both the components. So therefore when you look at the particle trajectory, yeah, so you will get an elliptical form of the water particle trajectory. So on the top you will see that because you have a horizontal this thing, it would be in this. So in between, yeah. So if you look at if you look at this trajectory to be some sort of a streamline, then whenever you draw the uh, tangent, okay, so the tangent will have a maximum value here and then goes on. Then here it would be vertical and so on. So this gives you the elliptical form of the water particle trajectory, which you can easily envision from this diagram. Okay, and uh, this can be got from integrating the u component and the w component of the velocities for over the wavelength and get this expression. And this has zeta by a. Zeta is nothing but the displacement in the x direction, and xi by b, where xi is nothing but the displacement in the z direction. So zeta by a square plus xi by b square is equal to 1, which is nothing but the equation of a ellipse. And obviously a and b are the semi-major and semi-minor axis of the ellipse. So this is the elliptical form of water particle trajectory. Now if you look at how this water particle trajectories vary when the depth varies. Okay, so for shallow waters where kh, that means 2 pi h by L is less than pi by 10, then you will see that it's more elliptical. And then when you come towards the bottom, you will see that mostly it is the velocity is in the horizontal direction. Okay. Now this has a large impact on the dislocation or disturbance of the sediments. It is something like scrubbing. So when we wash clothes, we take a brush and move forward and backward on the cloth, isn't it? We are scrubbing. So that scrubbing action takes place, and this is one reason why you have more sediment transport in the shallow waters. And as the water gets deeper and deeper, you will see that the trajectory becomes more and more rounded and the bottom component reduces. And for deep waters, for h by L greater than half, you will see that there is hardly any velocity component, and then the trajectory is circular here. So from elliptical, the trajectory gets transformed to circular, and here your a and b would be equal to 1, and this magnitude of a and b would go on reducing with the depth. So this is of course I haven't given the derivations for that. because of the paucity of time. And the other thing is that you have the hydrostatic and dynamic pressure components under the progressive wave. So obviously you make use of the Bernoulli's equation and then try to find out what is the pressure distribution. Then here you will see that you get the pressure to be equal to minus rho gz plus rho g h by 2 cos of kh plus z divided by cos of kh into cos kx minus sigma t. And here you can split it up into two components, that is P is equal to minus rho gz, which is the hydrostatic component. Okay, so which is the hydrostatic component, and please remember that this minus sign is associated with z because you are measuring z in the downward direction. So whatever value you substitute here, it should be minus, so this would become plus. And the other component is rho gz eta. Okay, so eta is this displacement. So depending upon whether it is positive or negative displacement, you have to substitute that here. And this kpz is equal to cos of kh plus z by cos of kh, which is called as a pressure response factor. Okay, so this pressure response factor is important. You could use uh, transducers which can measure the pressure, so you can put it onto the bed, and with that you would also be able to get information regarding the waves. Okay, so this is the pressure response factor kpz. Okay, of course this also would be there in your wave table. Okay, now coming to the last part, we will look at the potential energy and the kinetic energy. So if you take a wave and then take a slice of the wave here, then dPe, that means the differential potential energy, is equal to dm, which is elemental mass, into g z bar. What is z bar? Z bar is the distance of the centroid from the bottom. Okay, so this is the, because the datum we are taking is the bottom. Okay, then dm is nothing but the elemental mass, which is equal to rho into h plus eta. So h plus eta is this column into rho density into dx into 1. So volume would be h plus eta dx into 1. So volume times density is the mass. Then you substitute in this, and then when you integrate, yeah, so this is the expression that you have, and you will get the total potential energy to be equal to rho g h square by 2 plus rho g h square by 16. Okay, so this h is the depth of water, whereas this h is the height of the wave. Okay, so this rho g h square is nothing but the static pressure, and this pressure energy, and this is nothing but the pressure energy due to the wave, potential energy due to the wave. So this potential energy due to the wave is nothing but rho g h square by 16. Similarly, we can find out the kinetic energy. And how do you get the kinetic energy? It is nothing but half mv square. So m is for elemental kinetic energy, dm, half m dm v square. V square is u square plus w square by 2. Substitute, and again substitute for u and w, and then integrate it. You will get the kinetic energy to be equal to 1 over 16 rho g h square. So the total energy is nothing but the sum of the potential energy and the kinetic energy together. That would be equal to 1 over 8 rho g h square. So if you are able to determine what is the wave height, then you can estimate what would be the total energy per unit wavelength. Okay, so this is what you would have. Then you also have energy flux, which is nothing but, so what is flux? Flux is nothing but flow of energy per unit area per unit time. So when you do the calculation for that, that would be equal to E into C into N. Okay, So this E is the total energy that you have, and C is nothing but the celerity of the wave, and N is a factor which is the group velocity factor, and that is uh, N into C is nothing but the celerity of the group wave. So N is equal to Cg by C, you can substitute. Of course, this N also you will be getting it in the wave tables, which is equal to half of 1 plus 2 kh by sine 2 kh. Okay. So now when you have shallow waters, then what will happen is that this sine 2 kh is almost equal to 2 kh, and this would become 1. And for shallow waters, n is about 1. Okay. And for deep waters, this term would become almost 0, and n would be equal to half. So which means that the wave speed in deep waters is much less compared to the wave speed in the shallow waters. That is why the wave speed goes on increasing as it approaches the shore. Okay. So this is about the energy flux. Then you have the wave transformations. Basically, the wave transformations are, you have the uh, shoaling, the refraction and diffraction. And for that, we have the conservation of wave equation, which can be derived from eta to be equal to h by 2 cos omega, where omega is equal to kx minus sigma t. And since the crest occurs at omega equal to 2 n pi, the normal to this line n is given by del of omega. Now this del is nothing but the space derivative, and since this is a scalar, del of omega will become a vector, and since this is a vector, it will have a unit vector n, and this is the magnitude. Okay, del of omega, absolute value. So when I said space derivative, del, which is nothing but del by del x of I plus del by del y of j, then you can write k equal to n of del sigma to be equal to del of omega, and this is the governing equation. Del by del t of k plus del sigma is equal to 0. Okay, and then in this it is hidden that sigma is a function of x and y. It is not a function of t. Therefore, the constancy of wave period is also embedded in this equation. Okay, then if you take two rays, and then you can prove that the refraction is given by this sine theta by c equal to sine theta naught by c naught, which is nothing but the Snell's equation. So the Snell's equation gives you the refraction, and if you want to find out the height of the wave 2, that would be equal to the height of the wave at the deep water into root of C naught by 2 Cg into root of B naught by V2. So this can be proved using the Snell's law. So you have H2 to be equal to H naught into Ks into Kr. And what is Ks? Ks is nothing but the factor for shoaling, and Kr is nothing but the factor for refraction. So with this, you would be able to predict what would be the height of the wave if you know the bathymetry. Okay. Of course, computer programs are available to do these. Okay, I'll not go into those details. I'm just looking at the theoretical aspect here. Okay. Now, wave breaking would occur depending upon the beach slope. Yeah, and here important factor is what is called as a Iribarren number, which is also known as surf similarity parameter, uh, zeta to be equal to m divided by root of h by L. Okay, so depending upon whether it is less than 0.4, then between 0.4 and 2, and greater than 2, then you have the spilling breaker, the plunging breaker, and the surging breakers. So this is wave breaking phenomena. Then you also have what are called as wave diffraction. Supposing you have the incident wave which is moving from bottom upward, and let us say that you have some impermeable breakwater, okay, and this is the geometrically illuminated zone. Behind you have the geometrically shadow zone, and here what happens is that these waves turn inward, and this phenomena is called as a wave diffraction. Of course, I'm not going into the detailed expressions etc. of wave diffraction etc. because I think I have already utilized the time allotted to me. If you have any questions, I will try to answer. Yeah, over to the organizers.
Sir, thank you very much, sir.
Yeah,
Sir, actually, it was a very great session to understand the basics about this hydrodynamic state of the wave. Actually, we have some of the questions to be asked with you, sir.
yeah, please go
Actually,
ahead.
yes, sir. So one of the question they are asking is, what are the causes for the ocean circulation in the Bay of Bengal?
What are the causes for ocean
Ocean
circulation?
circulation in the Bay of Bengal.
Ocean circulation in Bay of Bengal, basically, it is the, uh, of course, the sea surface temperature plays an important role. In addition, if you look at the rivers, okay, so most of the rivers like the Ganga and the Brahmaputra, they discharge through Bangladesh into the Bay of Bengal. Okay, and because of this, you would get the ocean circulation in Bay of Bengal because you are asking specifically for Bay of Bengal, isn't it?
Yes, sir.
Yeah.
The next question is, they were asking about what is the importance of boundary conditions.
Yes. Without boundary conditions, you cannot solve any differential equation. Yeah. So even a simple uh, equation like the hydrostatic equation. Yeah. So if you take the hydrostatic equation like del P by del Z is equal to minus rho into G, isn't it? Or minus gamma. So when you integrate, what you will get? You will get P to be equal to minus gamma into Z plus C. Yeah. So when
Yes,
you integrate that, you get a plus C. Now, how do you get that plus C? You will get that C by putting the boundary condition. And what is the boundary condition? That P is equal to 0 and Z is equal to 0. Therefore, C is equal to 0. Yeah. So the boundary conditions are needed to solve the differential equation. And the number of boundary conditions required would depend upon the order of the differential equation. So supposing you have a second order differential equation, then you need two boundary conditions. Now in our case, what happened? We had a partial differential equation del square phi by del x square plus del square phi by del z square to be equal to 0. So you need two boundary conditions in x and two boundary conditions in z direction. So therefore, if you look at the earlier slide where you had A, B, C, D, where is that? Huh. Here, if you see, you have I think I missed it. Here, the top. A k k, the first line, if you see, phi is equal to a k, a cos kx, b sin kx, c e to the power of kz plus d e to the power of minus kz. So you have four constants, isn't it? So how do you evaluate these four constants? You need boundary conditions. So to get the constants, you need the boundary conditions. Yeah, any other question?
yes, sir. The next question they were asking is, can we take the sea bottom as a rigid one?
Yes,
The next question is there any any softwares that are available to predict the hydrodynamic conditions of the waves?
Plenty. Of course, I'm not a, numerical man. I'm more of an experimental person. But there are,
Thank you very much, sir.
yeah,
That's all from this questionnaire session. And I hope all the participants of our national seminar have been undergone with the complete knowledge of the basics of the hydrodynamics, sir. Once again, we have been very honorable uh, to show our thankfulness to you, sir. Thank you very
yeah,
much, sir,
yeah.
actually.
I thank the organizers and Dr. Lily for having invited me to give this talk on wave hydrodynamics. Thank you so much for all the participants for participating in this one-day national seminar. Thank you so much.
Thank you so much, sir. Thank you very
Thank you.
much.